Okay, so now that we have some basic Python background laid out for us, specifically, we know how to construct vectors, matrices, and manipulate them. We also know how to write for loops and if statements. What I want to do next now is combine this all together to a very simple programming example. So this is going to be a simple code which allows us to construct logic as well as to solve a problem that we want to go after, which is a root finding problem. And so hopefully this code illustrates how we might go about writing programs and how the Python architecture allows us to compute all the things we need inside of vector matrix structures encased in a logic structure. So let's go after this. So this is a very simple introduction. And remember, Python is a very broad language, but we want to focus just on simple things like matrices, vectors, which are going to be the backbone of doing scientific computing and data analysis and machine learning. So we're really focused on those as our objectives for currently. All right, so I'm going to do a root finding example, and this is going to be a root finding code. The Jupyter Notebook is available, so you can just look probably at the description of this video, and you'll find it on YouTube, and you'll find a link to where you can find this Jupyter Notebook to play around with and replicate what's going on here. So what is root finding? Well, root finding is a pretty simple idea, right? I have some curve, let's say f of x, and I would really like to understand where does it go through 0. So root finding is a very common thing to do mathematically. Often these roots mean something important to us, and so we're just going to set it up as a generic problem, which is if f of x is either data or it's some function, I don't know where the 0 values are, how can I use an algorithm to go through, search for this, and find it? Okay, so that is going to be the code we want to write. And you're going to see here, we're going to have to come up with some logic to get this. And so we're going to not only, first of all, flesh out the logic that we're going to have to use for this, but also think about then how would we build an algorithm to sort of encase that logic and go after this problem. Okay, so there's the value we want. We want the, I mean, obviously we can see it with our eye, that it's there, but the question is, how can I get this number and maybe get it to 6 decimal places or 4 decimal places, whatever accuracy requirements you have. We want to go after this and figure out an algorithm that will automate this process for us and actually get that value for us to some numerical precision. Okay, so how do we go about doing this? So first is some observation. First, just by looking at this, you know that at the value of x1, the curve is down here in the negative regime. F of x is negative. But at x2, it's positive. And what you know is the root is between x1 and x2, right? So you know it's between there, and you know what happens when I'm on the x1 side, it's negative, on the x2 it's positive, and somewhere in between it went through 0 and it's right there. So what we're going to do is we're going to do a bisection to get this. First thing we're going to do is say, well, okay, I know that the root lives somewhere in between here because on one side it's negative, on the other side it's positive, so that means the only way it could have gotten there is by going through 0. So we're going to try to write some logic around this so that we can have a code that will actually search for this point out and then get it to some prescribed numerical accuracy. So one possibility is to think about, in this interval, I know that it went through 0. So I'm going to go ahead and decide to just cut this interval in half and ask the question, out of that interval, is it in the left side or the right side? So the way the logic works here is if I cut this interval in half, I actually say, well, here's where I cut it in half, right here, it's the midpoint. Oh, the value of the function is still negative. So it still hasn't gone positive yet, which means the root is on the right-hand side. Okay, so what bisection is a method for root finding, which is I look at the interval, it's negative on one side, positive on the other, somewhere in there it went through 0, so I cut it in half and ask, is it on the right or left of that midpoint? And in this case here, you see it clearly, it's over here on this side, okay? All right, so this is what we want to look at. We're on the right-hand side now, and so what I've done now is I've shrunk my interval of where it possibly could be between x1 and x2 to now something that's half the size just between these two. So I've already made some progress. Could have been in this interval, now it's in this other half. So now I've cut that in half of where it could be. And what we're going to do is just continue to repeat this process. And this is where a for loop is going to come in very handy. Keep cutting it in half, keep cutting it in half, keep cutting it in half. Don't stop until you've converged. So that's the idea behind the root solving algorithm. Okay, so now, because if I cut it in half again, if I cut this in half, this green interval, I'm now here. Notice, oh, the value of the function is positive still in the side. That means it's between this yellow and this green. So notice now I've pinched this in. So the whole idea typically of root finding is to shrink the interval and trap the point somewhere in that interval so you can actually zero in on it and get it. So first of all, the thing that I want to highlight here as we've done this already, and I'm already, even if you just start sketching like this, you're going to start understanding what you need to do fundamentally. The first thing is we keep cutting it in half. So if I think about that, which is I'm going to keep cutting it in half, keep cutting it in half, that is a for loop. Keep doing this process. Cut it in half, cut it in half, cut it in half. Now we have to actually specify what it means to cut it in half and how to proceed, but that's a for loop. But notice also what happened. Every time I cut it in half, I have to ask a question. Is the 0 point on the right side or the left side? It's an if statement. So there's clearly an if statement, which says, if it's on this side, do something. If it's on this side, do something. Cut it in half. It's on that side, do something. This side, do something. So we know I have at least one if statement, and we know I have a for loop. So when I often talk about logic to people and structure, this is not rocket science. This is something that you can kind of think about for a little bit and have roughly an idea of how many for loops or if statements you're going to need to write your code ahead of time. So don't start writing code until you have some clear idea of what the logic sequence is going to be to actually do this. Okay? So that's another key point. Don't start writing code. Wait till you have a clear understanding of how you might construct it. How many for loops, how many if statements do you need available to you to actually even do something so simple as this? Okay? So you need to give that thought process time to make sure you understand this, and then you start writing code. You also have to understand, is the for loop on the outside and the if statement inside? Is the if statement on the outside, for loop inside? All that logic structure should be worked out in your head ahead of time or sketched on a piece of paper ahead of time before you start writing your code. Okay? So, summary. If I'm going to do this by section, there's one for loop. And here I said there's two if statements. And let me tell you about the other if statement. So one of the if statements is asking, am I on the left or right? There's one more if statement you want. You want it to tell it to, you'd like this thing to stop at some point, right? So the for loop, you could give it a prescribed number, but the other if statement is just going to simply check. What are you trying to do? You're trying to find the 0. So let me go back. You're trying to find this to be 0. What happens when you get this to be really close to 0? In fact, what if you prescribe, it's like, look, I only need my answer, I only need to be 0 down to 10 to the minus 4. So once you get it to 10 minus 4, you should stop. So there should be an if statement that says, if you're within 10 to the minus 4, stop. Get out of that loop. That's the other if statement. So the way to think about this is we could have counted ahead of time in this simple example. The logic structure would say there is a for loop. It's going to keep cutting it in half. Inside of that for loop, not outside, but inside, there's one if statement that says, the first if statement said, am I on the left or the right? Right? Which way am I going to move next in my iteration? And the other if statement says, well, if I've already got the solution, in other words, I'm accurate to whatever precision I need, like 10 to the minus 4, stop. So those two if statements sit embedded inside of the for loop. So let's build this. And let's draw some pictures. So first of all, the root finding, if I plot the function, let's make an actual function we're going to find roots for, okay? So what I had sketched there was just some hand sketch of a function. But now let's try to find roots of some transcendental, like e to the x minus tangent x, okay? So if I plot that function, here's what it looks like. It's the blue curve. So the orange curve is the 0 line. So first of all, you see there are quite a few zeros that I might have. Like there's one right here, right? There's one here. There's one right over here. There's one over here. So these are what we're actually trying to compute. So, and this is on the interval -10 to 10. So what we're going to first do is just say, okay, let's go after one interval to look at. In fact, maybe we can look at this interval right here. And I know that if I'm over here, I'm below, I'm negative, and if I'm over here, I'm positive. So I'm going to try to zero in on this one here. Notice also one thing important. Like if I just took this big interval and tried to do this bisection, there's multiple roots in there and this thing wouldn't work. So what I'm really trying to do is say, look, I know around where the root is, so let's go to that spot and then start to pinch it in and build an algorithm so I could get this point within some 10 to minus 5, 6, 4, whatever it happens to be, okay? So this is going to be my exact curve. I'm trying to find x values that make this curve 0, okay? And some of these transcendental functions actually show up in quantum mechanics. This is not just something crazy. This is something that shows up oftentimes for what are called quantum states or the eigenvalues of the quantum states. Okay, so let's go after this one right there. So there's my spot, and that's the one I'm going to try to actually zoom in on and try to get after. So how am I going to do this? So first of all, I'm going to look at two values. If on the left, x is -4, on the right, x -2.8. So these are 2 points around this that I want to like sort of try to see if I can pinch things in, okay? All right, actually, sorry, I think there's a little bit of a bug right here. Let me go back to here. At x2, it's here at -2.8, so right here, the value of the function, the right sent function, it's negative. At the left point at -4 is over here, and the value function is positive. So what I know is that between -4 and -2, it went from a positive number to a negative number. So I know that the root is in there between these two numbers. So we're going to start off with that basic fact. So let's decide how to build this algorithm. So those are going to be my start points. So here they are. I have the right point, which is -2.8. I have the left point, which is -4. In there is an interval where it goes from from positive to negative. Okay? So at least I have now, I've bracketed it into an interval I'm going to search in. Now remember, the midpoint idea is to just cut that in half. So let's automate this process. So first of all, I'm going to do a for loop. Remember, there's a for loop, 2 if statements. I start off with a for loop, and the for loop is going to be range going from 0 to 100. So it's going to take, it's just going to start walking, it's going to take 100 steps maximum. So that's what this thing is going to do. It's going to just start cutting it in half, cutting it in half, cutting it in half, cutting it in half 100 times. Now it could be I don't need to cut it in half 100 times because maybe I found the solution after 13 times. Then you would stop out of the loop before that. That's one of the if statements. Okay, so let's build up the structure. So the structure is, first I get the midpoint. Here's the midpoint, x of c. That's the center point. So what I mean by xc, it's like the x value of the center point, which is the average of the left and right point. Okay, so it's somewhere between -2.8 and -4. So that's the average value between them. And what I do at this point is ask the question, well, if I go halfway between, is my function positive or negative? So I can just evaluate my function at the midpoint. My function, remember, was exponent minus tangent. So I evaluate this at the center point, x of c. Okay? Now remember, my curve goes from, at -4, it was above. At -2.8, it was below. So now I'm going to do the logic structure here. So here's the curve f of c. I'm asking the question, is f of c positive or not? Okay? Now if f of c, if I go to the midpoint and it's positive, that means I haven't dropped below 0 yet. Because remember, at -4, I am at a positive value. Let me go back and show this. Remember, if I go halfway between and I'm still positive, it means I'm still over here on this side. I'm trying to get down to the negative side. So if this thing is positive, then the left point now is So the left point is now what my center point was. It means I haven't gone below, so my center point I picked, that's now going to be my new bracket, so that's going to be my left point. So I took the interval, I cut it in half, and it's like it's over here now because this is still positive. However, if that's not true, so else, there's only one option. It's either positive. If not, it's going to be negative. That means, oh, I went below 0. That means my right point comes over. So now that means, okay, I drop below. That means it's on the left side of the interval, which means I can take my center point is now my new right point. So I bracketed it. So you're basically doing with this command is you take this interval, you cut it in half. You're either going to take the left side of the interval or the right side of the interval. And that's what this does, depending upon if you cross the 0 line. That's all that does. You make a new interval. Okay? So that's step 1. And then you could just continue through the loop, right? You cut it in half, you pick, now, oh, it's this interval. Now I cut it in half, it's this interval, cut it in half, you keep doing that. So this is enough, and you would just, let's say, without this next if statement, you can run this 100 times and see where you end up. But what we're going to do is, after we've cut the interval, we're going to ask a very simple question. In fact, we could ask this question right away, right up here, right after we compute the f of c. Remember, we're trying to find the zeros of at what value of x is the function 0. So we're going to instead ask the following. If the absolute value of that function, in other words, at the center point, f of c, is less than some tolerance, and here I'm making this saying 1 to e to the minus 5. So if I have 5 decimal place precision, right? So in other words, and it's the absolute value is very important because you don't want to say if the value is less than minus 5 because you can have huge negative numbers. So the absolute value, make sure that whether the number is positive or negative, if it's less than minus 5, then what this does is first, it goes into this loop. If this statement is true, it goes into the loop. It displays that value of the point x of c, and it also displays the value of the function. And then you break. What this break command does, it gets you out of this loop. So you're in a for loop with j, and you're going to be in it 100 times. But if you do this and you keep cutting in half, and all of a sudden after nine times in the loop, you actually find that I actually have the solution to 5 decimal place precision, you cut out of that loop. You've converged. So again, all this is illustrating for us is a structure of logic. I have a for loop, 2 if statements. One of the if statements here continues to bracket and look at which side of the interval it's on. The other one says, was I successful at achieving my task? These 2 if statements are embedded in the for loop, which just says keep cutting in half. Keep cutting in half. Which side should I be on? If I've converged, stop. So in some sense, what this code sort of represents is what I like to think is a very simple and nice demonstration of logic structure in action. And so much of what you're seeing there is, right, we're going to be working with matrices, vectors, numbers, functions. Any function is always going to be represented as essentially some discrete number of values, which will be some array or a vector. And within that, we use our logic structures to accomplish tasks. This task was super simple. Find the zeros of a function. And as we'll go through this course, you'll see that our goals and our code are going to get more and more and more sophisticated. However, the code base we use still has this very basic logic structure behind it. We are trying to build code to accomplish a task. And you have to think ahead of time, what is the logic I need to accomplish this task? And this is the kind of way we would go about doing it. Python provides a really nice architecture to do this. And this little example here, which you'll have access to the Jupyter Notebook, allows you the ability to play around and manipulate and start to understand what you're going to have to do coding-wise to build logic structures for accomplishing your tasks.